In this session, we continue with our discussion of the differentiation rules, and we will cover the rule for products of functions, which is called the product rule. And so the question is, if I have u, which is differentiable at x, and a function v, which is differentiable at x, and y is the function given by the product, u times v, what is the derivative of y at x? Okay, so we again construct the difference quotient and we take its limit to find the derivative. So y of x equals u of x times v of x. Y of x plus h is equal to u of x plus h times v of x plus h. Now if we take the difference, y of x plus h minus y of x, we will get u of x plus h times v of x plus h minus u of x times v of x. Now that's not particularly useful to us because what we are expecting is to get the answer in terms of the original functions u and v and their derivatives. So I want to see the difference of u and the difference of v coming up. So I can get that by adding and subtracting a term u of x plus h times v of x. Okay, so I get u of x plus h, v of x plus h, minus u of x plus h, v of x, plus u of x plus h, v of x, minus u of x, v of x. Now this has the advantage then that I can group my terms so that I get u of x plus h times the difference in v, v of x plus h minus v of x, and the difference in u of x plus h minus u of x times v of x. Now I know what happens when I divide these differences by h and take the limit, I will get the derivative. Okay, so now we divide by h to get the difference quotient. So y of x plus h minus y of x over h is u of x plus h times the difference quotient for v plus v times the difference quotient for u. Now we're going to take the derivative. Sorry, we're going to take the limit as h goes to 0. Well, the limit of a product is a product of the limits, so you get limit of h as h goes to 0 of u of x plus h times the limit as h goes to 0 times the difference quotient for v. And v of x doesn't involve h, so it can be pulled outside of the limit sign, times the limit as h goes to 0 of the difference quotient for u. Now u of x plus h, u is differentiable at x, so it's continuous at x. So the limit as h goes to 0 of u of x plus h is just to u of x. The limit as h goes to 0 of the difference quotient for v is the derivative of v at x, plus v of x times the limit of the difference quotient for u, which is the derivative of u at x. So you get that the derivative of u times v is equal to u times the derivative of v plus the derivative of u times v, and provided that these individual limits, derivative of u and derivative of v, exist. So that's the product rule. So let's do an example. Suppose that y of x equals 1 plus 2x times 3 over x. So then this is the derivative of y is the first function times the derivative of the second function plus the derivative of the first factor times the second factor. So it's 1 plus 2x times the derivative of 3 over x, which from the previous rules is minus 3 over x squared, plus the derivative of 1 plus 2x, which is 2, times 3 over x. Okay. There is no need for you to simplify or manipulate the expressions after you get something like this. Okay. Now, just as an exercise, you don't really need to have a rule for 3 factors in the product, because you can just apply your product rule twice. But supposing, just as an exercise, w of x is equal to f of x times g of x times h of x. We want the derivative of w. Okay, we can group w as one factor is f of x times g of x, and the second factor is h of x. So this is we can take the derivative of f times g times h of x plus f times g times the derivative of h. Okay, the derivative of f times g is given by the product rule times h of x plus f of x times g of x times the derivative of h. And then we get f of x times g of x times the derivative of h plus f times the derivative of g times h plus the derivative of f times g times h. Okay, so that has a pleasing pattern to it. You can find the derivative of w of x, which is 1 plus x cubed. Think of it as 1 plus x times 1 plus x times 1 plus x. So it would be 1 plus x times 1 plus x times the derivative of 1 plus x, which is 1, plus 1 plus x times the derivative of 1 plus x, which is 1, times 1 plus x, plus the derivative of 1 plus x is 1 times 1 plus x times 1 plus x, which is 3 times 1 plus x squared. Okay. If you had a function f of x is equals 1 over 1 minus x squared, okay, you can think of that as 1 over 1 minus x times 1 over 1 minus x. So the derivative would be 1 over 1 minus x times the derivative of 1 over 1 minus x, plus the derivative of 1 over 1 minus x times 1 over 1 minus x, which would be twice 1 over 1 minus x times the derivative of 1 minus x. Okay, and if we do that, we get 2 over 1 minus x cubed. Okay, continuing with this, let's say we wanted to do a linear approximation at x is equal to 0. The function at 0 is 1. At the derivative at 0 is 2 over 1 minus 0 cubed, which is equal to 2. And then the linearization is given by the function at 0 plus the derivative of the function at 0 times x minus 0. And that's equal to the function value at 0 is 1 plus the derivative value at x equals 0 is 2 times x. Okay, so for small x, that is for x close to 0, f of x is approximately equal to L of x is equal to 1 plus 2x. That's the equation of the tangent line on the graph at the point 0, 1. Okay, so we now have the product rule, and in the next segment we are going to go on to the rule for quotients of functions.